So organic synthesis and arenes, question 4 also will do. In question 4, structure which was proposed by Kakule, benzene is now thought to have a delocalized structure. Evidence for delocalized structure, the benzene includes only one structure of a 1,2-dichlorobenzene and analysis of X-ray diffraction. Explain why each of these makes delocalized electron structure more likely to correct than Kakule. So the thing is, why 1,2-dichloro structure is there, and then the X-ray diffraction, how it proposed. So if we say 1,2-dichlorobenzene, so evidence for a delocalized structure of a benzene include only one structure of 1,2-dichlorobenzene. Like only one possibility is there that we have 1,2-dichloro. If the double bond will break, chlorine might attach here and chlorine might be attached here. So how it can, if we check the isomers of a dichlorobenzene in which one has a single bond between the carbon atoms and the bonded chlorine and the other have a double bond, we don't find them. So we don't find like the structure in which the benzene is having, because according to Kakule's model, it should undergo addition reaction. But actually what will happen? Actually what happened that it undergoes substitution reaction. And when it has a substitution reaction, it means like it proposed that there is a delocalized electron, because delocalized electron systems support the substitution reaction rather than addition reaction. And the second one, analysis of X-ray diffraction image of a benzene. When we pass X-rays and we work out when we work out the bond length, we found that the carbon-carbon double bond and the single bond, they all have the same length. Like this bond length of C double bonded with C and single bonded C all are same, the X-ray diffraction. So only one structure of 1,2-dichlorobenzene and the X-ray analysis shows the like Kakule model is not correct. Otherwise, what might happen that, for example, one structure of a 1,2-dichlorobenzene is there. What this means? This means like when addition is happening, like when we add chlorine would be added across each bond. When we do addition reaction, like chlorine must be added to each bond. Like it will break down all the. According to Kakule, it should be highly reactive as the double bonds are there. So addition reaction will occur and all the bonds will break and a chlorine will be added. But chlorine can be in the position other than 1 or 2 as well. So that is also an evidence of a delocalized electron rather than a Kakule's model. Phenol has a delocalized structure. Compare the condition and the product of a reaction for bromination of a phenol and benzene. So phenol, when phenol is reacting with a benzene, with bromine, and when benzene is reacting, the reaction conditions are different and the products are also. First thing, benzene, because of the delocalized electron, it is highly stable. It does not readily react. So when a phenol reacts with a bromine, it can react with room temperature. This can react around 60 degrees centigrade. When this react, it will undergo multiple substitution, like example 2, 4, and 6 tribromophenol is there. Multiple substitution can occur. But when a benzene react, it's a mono substitution, like only one hydrogen will be replaced and one bromine is added. And here we don't need a catalyst to for this reaction, but we need a catalyst here. So reaction, you have to compare the reaction chemistry, like the temperature, the products, the reaction conditions. Benzene can be converted into ethyl benzene in electrophilic substitution. So we want like a carbon chain, alkyl chain. So it's a similar reaction as we did in the question 3. We produce electrophile. So when carbon changes, we want to add a like C2H5 we want to add. So C2H5 and then Cl plus AlCl3. As a result, what it will produce C2H5, the electrophile, plus AlCl4 with a charge -1. And this C2H5, the electrophile, will attack on the benzene ring. And the bond will break. And one side will have C2H5, another one will have H. And this hydrogen will break. As a result, the alkyl group is added, alkylation of a benzene plus H plus. And what happened to this H plus? This H plus will combine with AlCl4 with a charge minus, and it will produce AlCl3 plus HCl. This is a reaction mechanism for the electrophilic substitution reaction of a benzene. Alkylation of a benzene, you can also say. When ethyl benzene is dehydrogenated, it forms a phenyl benzene. So if we dehydrogenate, means like we remove hydrogen and it turn into phenylethene, sorry. Ethyl benzene turn into phenylethene. Predict one wave number range where infrared spectrum of phenylethene would differ from infrared spectrum of ethyl benzene. So this was ethyl benzene. C2H5 means like this will be CH2, this will be CH3. So which wave number is different? You can use a data booklet. As you can see here, the main difference is the double bond. Like here, there's a double bond, here single bond. So this double bond, C double bonded with C, and check the data booklet for this and write the wave number accordingly. Write equation for polymerization of phenylethene. So phenylethene, alkene is there, so it will undergo addition polymer. What you simply have to do addition polymer, you just have to break the double bond. And this is an equation. So equation, we have to involve reactant product both. This will be CH and this will be CH2. And we put a bracket and write N, and here also N. So this is the equation for the polymerization of phenylethene. So this was question 4, sorry, related to organic synthesis and arenes.